So mod 2.4 is going to be taking that constant rate of change stuff, and it's going to be elevated and talk about it more. Now, remember, there's some equations that we need to make sure that you have listed and you're using. So I'm going to write them down at the top just so we remember them as we go. So three equations that you should always know when we're talking about constant rate of change. So one is that the slope is the change in y over the change in x, or y2 minus y1 over x2 minus x1. Another one is that the change in y we can always find by taking the slope times the change in x. Remember where that m is that constant rate of change. And then a good equation, if you're looking for an equation or a formula to use for that particular situation, your point slope formula is always a good one to go. So it's y equals y minus y1 equals m times the quantity of x minus x1. So those formulas are going to appear in all of chapter 2 again and again and again and again and again and again and again. So I can't stress enough how important those formulas are. So we've got here our slope equation. We have how do you find that change in y if we only know the change in x? And then if we want an actual formula to fit the entire situation, point slope is a really good option. Now you can use that y equals mx plus b, but this one tends to fit more situations, so I do tend to encourage that. Okay, so in this lesson, the main difference is we're going to talk about constant rate of change as a proportionality and how those two quantities are changing proportionately. And so that's kind of going to be the difference that we're going to see. Okay, so any questions about the formulas we've got so far? Okay, so let's take a look at this picture here. It says a nurse has liquid medicine that must be diluted precisely before giving it to a child. The nurse mixes 2 ounces of concentrate medicine with 3 ounces of water based on the manufacturer's instructions. The circle marked on the cylinder represents the height to which the 5-ounce mixture rises on the cylinder. Shade and label the drawing to indicate the part of the 5-ounce mixture that is concentrated medicine. So it says that we have marked, so I'm going to put it in one color. That 2 ounces would be the medicine. So that means that 3 ounces would be the water. Now, if we have one child, which maybe let's say is a 2-year-old child, and that 2-year-old child gets that 5-ounce mixture, but say a 9-year-old child, bigger, needs more medicine, and in that case, the mixture might be changed. Now, here's the example. It says in part B, what if the nurse needs to make a 15-ounce mixture? Okay, so let's assume, here's 5 ounces. So there's 10. Let's say 15 is about here. Now, we're just guesstimating, but let's put a little circle here, and let's mark that as 15 ounces. Now let's think about how we would need to break down the medicine for that larger child for a 15-ounce medication. So we know that it always has to be a 2 to 3 mixture, okay? So there's a number of ways to do it, but what we can say is, let's talk about just the medicine first. If 5 ounces, we use 2 ounces of medicine, then 15 ounces total would be how much medicine? So we'll call it M for medicine. That's where the proportionality comes from, okay? So what we're going to do is to solve a proportion. The quickest way to solve a proportion is to cross multiply. So 5 times M would equal 15 times 2, or 30. And so then to solve that, we have to divide both sides by 5. So there has to be 6 ounces of medicine. Now, another way to do it, if we multiplied this by 3, so that became 15 ounces, then we have to multiply each of those by 3. So it should make sense that we would get 6 for the medicine here, and we would get 9 ounces for the water here. So that proportionality has to be maintained. So that's one great thing. Since I multiplied this by 3, you should see the same thing happen to these measurements. That got multiplied by 3. That got multiplied by 3, okay? So I'm sorry my word ounce doesn't look like anything. That's ounces, ounces. They look like they're 50s and 150s. I apologize. I'll try to write it like that from now on. Okay. So anyway, so that is a good way to solve problems like that. Those rules of proportionality are very helpful, okay? So then let's look at E. So we already did B. No, I'm sorry, let's look at C. It says for every 6 ounces of concentrated medicine, the mixture must then take on 9 ounces of water. This is because 6 ounces of medicine is 3 times as much as 2 ounces of medicine. So the amount of water will need to be 3 times as much as the 3 ounces of water we started with. So that's all they're saying for C. And we kind of did that logically up above as we were going through that process, okay? So D says, true or false? The amount of water needed for 3 ounces of medicine is 1.5 times as large as 2 ounces of medicine. So the amount of water needed is 1.5 times as large as 3 ounces of water, or 4.5 ounces of water. So that's true, because that proportionality will always change. So if you did 1.5 times the one piece of the medicine, then the 1.5 times the water would also be what you would have to do, okay? If we move on then to E, it says, after mixing the original 2 ounces of medicine and 3 ounces of water, the nurse is directed to give the patient 8 ounces of the mixture instead. You see the nurse adding 3 more ounces to the 5-ounce mixture, adding 1.5 ounces of concentrated medicine, and adding 1.5 ounces of water. Is the patient's dosage accurate, too strong, or too weak? Now remember, here's the problem with what the nurse has done. These 2 things are the same. The water and the medicine should never be the same. Remember, it should always be that 2 to 3 proportion. So in this particular case, we've put too much medicine in there, so it would actually be too strong. Okay? So hopefully that kind of makes some sense. Okay, so now let's move on to number 2. It says, using the context from the first thing where we've talked about the medicine we've mixed, a nurse has liquid medicine that must be diluted precisely before giving it to a child. The nurse mixes 2 ounces of concentrated medicine with 3 ounces of water based on the instructions. How many ounces of water will be needed? Now, this is what's great. We know that it should always be a 2 to 3 medicine. Well, let's do it the other way. Let's do 3 to 2. Let's do 3 to 2. So water to medicine, okay? So that would be our change in y over change in x, okay? So if we want to know the change in y, we can just take 3/2 or 1.5 times our change in x. So this is going to allow us to fill out the chart very quickly, okay? So here's why. So here, Do you see how we've gone backwards 1? So our change in x is -1. So our change in y is going to be 1.5 times -1, or -1.5. So we have to change the y by going back 1.5. So that's why it will be 1.5. See how that worked? We can use that formula. Okay, now let's look at our change in x here. Our change in x here, what happened to that x? It went up 3. So our change in y will be 1.5 times +3, or 4.5. So it has to go up by 4.5. So just take 3 plus 4.5 to become 7.5. And we can keep doing that, okay? What is our change here? We've gone up by 7. So our change in y would be 1.5 times 7. 1.5 times 7, I think, is 10.5, but let me just verify that. 10.5. Because it's a positive change, we have to take where we started, 7.5, and add 10.5. 7.5 plus 10.5 is 18. And if we kept checking this ratio, 18 to 12 should be 3/2. And then our final one, let's do it one more time. So we've gone up by 5. So our change in y would be 1.5 times 5. It should go up by 7.5. So we left off at 18. We need to go up by 7.5. So we should now be at 25.5. Now, you should be able to check your work on a calculator very quickly. 1.5 divided by 1 should be 1.5. 3 divided by 2 should be 1.5. 7.5 divided by 5 should be 1.5. 18 divided by 12 should be 1.5. And 25 divided by 5, or 25.5 divided by 17 should be 1.5. So, and there's other ways to do it. You can use a proportion each time. That does work as well. But that's just a little way to fill out the chart using that delta y over delta x, okay? So it says, write instructions for the nurse so they know how much water to add when they know the amount of concentrated medicine that they should use. And so if we know how much medicine, so if we know the medicine, if we multiply it times 1.5, we will get the water. Or you could even have said 3/2, that's okay. So the medicine times 1.5 should always be the water. And we could have even done that up here each time. 1 times 1.5, 2 times 1.5, 5 times 1.5. That's another way to fill out the chart. Write a formula to determine the volume of water to add to X ounces of concentrated medicine. So now let's use just the variables they talked about. We're going to have X to be the medicine. We're going to have Y to be the water. So Y is going to be your delta X, or I'm sorry, your slope times X, and that's why it's Y equals 1.5 times X, or 1.5X. Now I noticed in iMath that they sometimes will give you the variables they want you to use. So make sure you're using those. Don't just use a random X and Y, but you're welcome to use X and Y at first and then put in the formula, the variables that they're talking about. Okay. Now it says to create a graph that represents the volume of water needed in terms of the volume of concentrated medicine. See how that says in terms of the concentrated medicine? So we know that our X is going to be the amount of medicine in ounces and we're going to have Y is going to be amount of water in ounces. Okay? So, of course, if we have no medicine, we have no water. Let's put in, let's go with 2, because we know initially, remember that one that we had a total of 5? That was 2 ounces of medicine became 3 ounces of water. So if we go to the point 2, 3, this point right here, that's going to be that 2, 5 situation. Now, do you remember we also did when it was 15, that 2, 3 became, that became 6, 9. So we should be able to go over 6 over, and 9 up. And it should line up. See how it lines up? And then let's just make our line. Now, the reason we don't have negatives for this is we're not going to have a negative amount of medicine. Either we have medicine or we don't. So many times you'll notice these application problems occur in the 0, 0 section of the graph. So that's pretty common. And then E says to explain the points on the graph. So let's talk about that. Now, if you think about it, each point on the graph represents a volume of medicine that corresponds with a volume of water. So it's the volume of medicine that corresponds with a correct volume of water. So what you sometimes see is sometimes if you have, so there's less mistakes mathematically. Sometimes you'll even have a table for the nurses already kind of set up. But some of the older medicines and some types of medicines, they have to do this themselves. My sister is a pediatrician, so she always has to base any medicine that she gives to a child based upon their weight. So there's a separate even calculation there. So that sometimes comes into play when it comes to kind of a nursing application. Do we have any questions about any of the things we've seen so far? Okay. So here, there's not much, you don't have to write anything down, but if you want to highlight a few things with me, it says in a proportional relationship, 2 quantity values are changing so that they remain the same relative size. One feature of proportional relationships is that the 2 related quantities must scale together to maintain the proportional relationship. So like if we see here, let's look at this little baking example. If the recipe calls for 5 cups of flour is going to give you 3 cups of sugar, if you quadruple everything, then so if you multiply by 4, 20 cups of flour has to be 12 cups of sugar. So it's really just always going to maintain that relationship. The ratio of flour to sugar is always flour, the 5 on top, 3 sugar, the sugar on the bottom, okay? So proportions are nice. They allow us to solve those types of equations very easily and very quickly. It depends on how you want to think about them. So I'm going to show you one way to solve these problems. There are multiple ways, so know that there are multiple ways to do this. Okay, so now let's continue. Let's take a look at number 3. So it says here are 2 cylinders, one wide and one narrow. Both cylinders have equally spaced marks for measurement. Water is poured into the wide cylinder, so I'm assuming that's this one, and it goes up to the 2 mark. This same volume of water rises to the 7th mark on the skinny one. So let's put a little 7. There might have been a 7 that I might have missed, but let's put a little 7 right there. Okay. It says both cylinders are empty. The water is poured into the narrow cylinder up to the 13th mark, how high would this rise if poured into the empty, wide cylinder? Okay, so I'm going to show you 2 ways to solve this problem. What you can think about the fact is it's always going to have a wide to narrow ratio of 2 to 7. Okay, so if we think about, now if you put narrow to wide, you would have 7/2. So whatever relationship you held that's the one you're going to do. So if wide over narrow is always 2/7, remember we stuck 13 into the narrow. So, wherever 13 is here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We're asking how much has to go into the wide that would be proportional. So the narrow goes in the bottom, the wide goes in the top. So I'm going to make that a W for that. Okay. So mathematically, to solve that, we just have to multiply by 13. So the wide is going to be 2/7 times 13. We could also say that, we can also use that 2/7 similar how we would use a slope, okay? So mathematically, if you just said it was 26/7, that's fine. If you wanted to draw a picture of that, 26/7 is a funky, yucky decimal. It's about 3.7. So, you could just try to get under the 4 a little bit. But the way that you mathematically could show it is you could just put 3.7. Okay. So then if you look at I, when it says X represents the height of the water in the narrow one, and or X is the water in the narrow and Y is the water in the wide, do you see how they set up a little proportion here? Okay, so let's write that down a little bigger so we can talk about it. So remember how I said that's narrow, or that's wide, I'm sorry. Wide to narrow should always equal wide to narrow. It should always be a fractional relationship that would reduce down to 2/7. Now, if you had decimal values, 2/7 is the decimal 0.2857, whatever that is, okay? That's why that fractional 2/7 is so much more powerful. So if I multiplied the width by 2 and got 4, I know that the narrow must be also multiplied by 2. So it would go up to 14. If I multiplied the wide and made it 6, then I know the narrow should be 7 times 3 and would be 21. So whatever you do to the top, you would also do to the bottom, because that's how fractions are equivalent. Okay. Were there any questions about this proportionality as far as this? Yes.
Maybe this is just me, but how do you come up with the idea to make the fraction like that? Like, how does it even come to your mind to put it wide over narrow?
So you don't have to keep it wide over narrow. So that's a good question. If you decide, because there is a relationship somehow that relating the wide and the narrow cylinders. So you can decide to put it narrow over wide. I could decide to put it wide over narrow. It doesn't matter, as long as if I put it wide over narrow on one side, then like if you put wide over narrow, you would do y over x like you see here. But if you did narrow over wide, yours would be x over y equals 7/2. So you are allowed, because of it, that proportionality, to use the fractions will work either way. So if you do the wide on top and I do the narrow on top, as long as you're consistent on both sides, you're going to get it to work, okay? It's about consistency for these proportional ones. Okay, and the last one I wanted to do, because I saw this in quite a few of the applications, was the the candle kinds. I've seen quite a bit of the candle ones. Now, one of the things I wanted to talk about for the candle problem was the fact that it says that it's burning at a constant rate of 1.8 inches per hour. Is the candle, as it burns, is it getting taller or is it getting shorter? It's getting shorter, right? We know that instinctually. Here's the part that we mess up mathematically. That means that our rate of change, so we'll call, so that would be, the rate of change would be the remaining length per unit of time. It is going down by 1.8 inches per hour. So one of the things I noticed when I was helping some people is that we're forgetting the fact that it is shortening in length. So make sure you're making that rate a negative to reflect that, because that's a very common mistake, okay? So the negative 1.8 represents, in this context, it's representing the change in the height in inches per hour. And it's negative because it's getting shorter. Okay, so that's the main takeaway there. I noticed that a lot of people were not including the negative. Okay, they would see the positive 1.8 there, but when they actually made the equation, they weren't making that negative. So be careful with that. B says, what does the expression 1.8t represent in this context? 1.8t, the time, and the 1.8 times the time would be the amount of change. So that is the total change. You'll notice they didn't include the negative there because they're just talking about what does that particular thing mean, okay? So C says, what does the expression 17 minus 1.8t represent? That is the height at any particular time t. So that's the height. Now, why is that the height? So let me draw my beautiful candle here. Okay. We got a candle. Okay. It started out at 17 inches. Okay. Every hour, it's going down by 1.8 inches. So at some particular time, it has gone down by 1.8 t. So this remaining light, that remaining is 17, take that off. So that's the height at time t. That's what's left. Okay. Actually, you could say this would probably be, you could write that as a positive 1.8. I'm sorry. I think I accidentally turned in some kind of weird, I don't know. Anyway, that's 18 t, or 1.8 t. Okay. And how do we know that that's correct? Well, think about that. Should total the original 17 in height. 17 minus 1.8 t plus 1.8 t, that 1.8 would cancel out. So is this proportional? That's what it says in D. Is that proportional? And the proportionality occurs when we have a constant rate of change. So that would be yes. Delta R over delta T is always negative 1.8. So if something is changing at a constant rate of change, it's always proportional at a certain time. You would say yes, it's proportional. And then it says, is R proportional to T? Well, in that particular case, let's say at the beginning, say we've gone an hour. How you can check proportionality? Let's do that. Let's say we've gone 1 hour. I was 17 inches. I've gone down by 1.8, 17. So at 1 hour, I am now at 15.2 inches. At 2 hours, I am at 13.4. So how can you check if the plain old R and T, so this is T and this is R, how can I check to see if those are proportional? If they're proportional, 15.2 divided by 1 should be the same as 13.4 divided by 2. Well, 15.2 divided by 1 is 15.2. 13.4 divided by 2 is 6.7. Are those numbers the same? No. So it's not proportional. Another way to think about it, if you think about the equation for this particular problem, let's write an equation. The equation for this problem, I didn't write it down, but is R equals 17 minus 1.8t. A proportional equation should always be of the form A over B equals C over D. That is not that type of equation. The rate of change, the slope, you can write like that. So that particular part of the equation is proportional, but that particular equation relating the original height with the height over time isn't proportional. So that is a little bit about that. So do we have any questions about number 5? Yes.
How do you get the idea of delta R and delta T, and then what exactly is the difference between that and then the regular variable?
Okay, so let's look. Do you see this right here? Do you see how it's a constant rate of, and then it's going to always use the word per. That's going to be your kind of your marker for your slope or your deltas, my change in. So if you see a something per something, that would be your delta, and this would be your first, the delta thing on top, so inches, and this would be our delta thing on the bottom, so time. So they called the amount of inches at any particular time R, and they chose T. Now, if you called it something different to change, you're okay. I'm okay with that if you kind of explain what you did. But that's really the good marker as to what it's telling you. If it has a starting value other than 0, so this one had a starting value of 17, that tells you that the whole equation isn't proportional. Proportionals equations always have to start at 0, 0, like the one we saw, this one up above, about the medicine. You either have medicine or you don't. So you start at that 0, 0 spot. But because this one started at 17, it actually kind of messes that up. So your rate of change, just look for the inches per hour, miles per second, whatever the two things. If they use that word per, that's a really good marker as to what they're talking about.
So is this question just sort of to show that you can still have delta and the variables and they answer two different things?
Yes, exactly. Do we have any other questions about this or any of the other ones? Yes.
I'm confused on how the rates of changes are proportional.
So a rate of change, let's look at the change in R over the change in time, and I think that's going to help you. So this here, I did an R and a T. Okay, let's do a delta R and a delta T. Okay, so if I know that I have burnt the candle for 2 hours, so that is my change in time. My candle will have gone down 3.6 inches. let's say instead I burn the candle for 3 hours. Actually, it would go down 3/6 inches. Let's make that negative to reflect that. It would go down by 5.4 inches. If we do delta R over delta T in either of these particular cases, we would get equal values. Each one of those is negative 1.8. So that's a really good way to think about it. If no matter what you pick, and you did that delta R and delta T, and you always get the same thing, then that would be a constant rate and a slope, basically. So it represents a linear equation, but that is just how that particular one is changing. So it happens to be slope. A proportional equation will be a slope equation that starts at 0, 0. So if the whole equation is proportional, you're starting at 0, 0. That's the way to go. Please turn these in. Don't forget the things that are due in iMath, okay? I will see you tomorrow.